Hello, I am Genevieve Schroeder, and I am a third-year PhD student at Northwestern University, working under Wenfei Fong. Today, I will be presenting my results from my recent paper about the search for Magnetar Emission from short gamma ray bursts. Gamma ray bursts, or GRBs, are very energetic explosions that occur throughout the universe, and they are divided up into two categories based on their duration, long and short GRBs. Long GRBs have durations longer than 2 seconds and are connected to the core collapse of massive stars. I will be focusing on short GRBs, which have durations less than 2 seconds and have the suspected progenitor of a binary neutron star merger. This association was shown when LIGO detected its first binary neutron star merger, GW 170817, at the same time and location that GRB detectors observed its electromagnetic counterpart, GRB 170817. So, the picture we have is two neutron stars that merge, and they create some merger remnant as well as a short GRB. But what is that merger remnant? This is dependent on the mass of the two neutron stars that merged, and therefore the mass of the merger remnant, as well as the neutron star equation of state, which determines the maximum mass of a non-rotating neutron star, also known as the Tolman-Oppenheimer-Volkov mass, or MTOV. If the merger remnant is much more massive than this mass limit, it will directly collapse into a black hole, and if it is less massive than this mass limit, it will remain a stable neutron star. However, if the merger remnant is just above this mass limit, it can exist as a temporarily stable neutron star, either a hypermassive neutron star, which is supported by differential rotation, or a supermassive neutron star, which is supported by solid body rotation. In addition to this merger remnant and resulting short GRB, a binary neutron star merger will create a kilonova, which is an ejection of very massive particles that radioactively decay. Now, let's suppose that the merger remnant is some type of neutron star, either indefinitely or temporarily stable. A typical neutron star already has a pretty high magnetic field strength of about 10 to the 13 Gauss. So, you can imagine that if two neutron stars merge together, the resulting neutron star can end up with an even larger magnetic field, say 10 to the 15 Gauss. This is a magnetar, which is just a highly magnetized neutron star. We haven't yet detected a magnetar that has come from a binary neutron star merger, but recent short GRB 200522A, which the Fong group also worked on, has shown promising signs. The magnetar remnant that was produced in the merger will spin down very quickly due to processes like magnetic braking, and in doing so, it will lose its rotational energy. If the magnetar is hypermassive, it will spin down too fast and collapse into a black hole before losing much of its energy. But if the magnetar is supermassive or indefinitely stable, it will be able to lose a significant fraction of its energy as it spins down. This energy has to go somewhere, so it is deposited into the kilonova ejecta, which energizes the kilonova and in turn produces synchrotron radiation. This synchrotron radiation will peak in the gigahertz radio bands on the order of years after the burst and merger, and is exactly the emission we were searching for. My paper presented 9 new late-time radio observations of short GRBs at 6 GHz using the Very Large Array. We required that these bursts must be at a redshift of less than 0.5, which are the most nearby short GRBs, because these nearby bursts are the most promising for detecting magnetar emission. These observations occurred 2 to 14 years after the bursts, and while these observations were very deep, with 2 hours of observation for each target, we did not detect anything at any of the locations of the GRBs, placing upper limits on the flux at these locations. Additionally, we searched the literature and gathered a sample of 18 other late-time radio limits of short GRBs at around 6 GHz. In the figure on the left, we are looking at luminosity versus time. Our sample of 9 short GRBs is represented by purple triangles. The 18 other radio limits are seen as gray filled-in triangles, and gray empty triangles are late-time observations at other frequencies. GRB 170817 is represented by the gray filled-in and hatched triangle. In addition to taking some of the deepest late-time radio observations of short GRBs to date, We also improved upon the current light curve modeling of the late-time energy injection of kilonova. Our light curve model properly incorporates relativistic effects and can be seen as the purple lines on the plots for different interstellar medium densities. The 4 panels represent the models for 2 different masses, a typical kilonova ejecta mass of 0.03 solar masses and a maximum ejecta mass of 0.1 solar masses, as well as 2 energies, 10 to the 52 ergs, which is the energy expected to be extracted from a supermassive magnetar before it collapses into a black hole, and 10 to the 53 ergs, which is the maximum energy that can be extracted from a stable magnetar. Now, the physical parameters of these GRBs are difficult to determine, so we created a grid of light curves to visualize the energy density space of each GRB. We created 62,500 light curves for each GRB for different pairs of energies and densities, and found the flux of each light curve at the time of the radio observation. You can see this in the plot on the right, where the solid purple line is the radio flux upper limit of the observation. The purple shaded region is either the determined density region for the burst or the typical density if no density could be determined. And the triangle represents our upper limit at the median of the density region. Since there is no detection for any of the 27 GRBs in our sample, these lines and triangles represent the absolute maximum energy that could have been deposited into the kilonova and still be consistent with our non-detection. Also, the black dashed line is the previous analytical model, so you can see how our model is much improved in the low-density, high-energy regime, which is where relativistic effects come into play. Now, we can take these energy density grids and turn them into probability and cumulative distribution functions to see how our maximum energies line up with the predictions. Since for 11 out of the 27 bursts in our sample, we did not have a density constraint, we chose to display the distributions both with and without a density prior. The distribution with the density prior is seen as the solid purple line, and the distribution without is the dotted purple line. A reminder that these distributions are upper limits, hence the arrow pointing toward lower energies. These distributions are superimposed over the ejecta energy distributions expected of a binary neutron star merger, based on various values of MTOV. These predicted distributions are bimodal, and on the lower end is the ejecta energies of around 10 to the 50.5 ergs, where normal kilonova ejecta energies with no magnetar contribution reside. And on the higher end of the bimodal spectrum is ejecta energies of around 10 to the 52.5 ergs, where boosted kilonovas from magnetar energy deposition reside. You can see that if MTOV is high, you will be more likely to have a binary neutron star pair that creates a stable magnetar remnant, and therefore have a higher ejecta energy. We can compare the GRB ejecta energy distribution with the predicted ejecta energy distribution to rule out MTOV of 2.4 solar masses in the higher ejecta mass case, as well as MTOV of 2.3 solar masses in the lower ejecta mass case. GW 190425, a recent binary neutron star merger with no GRB counterpart, does change these predictions. The predicted distributions on the last slide were created using our galactic double neutron star population, which was well in line with the masses derived from GW 170817. However, GW 190425 changed our understanding of the masses of binary neutron stars because its total mass was 5 sigma higher than the median mass of our galactic population. So, in order to incorporate the potential for higher mass binary neutron star mergers into our distributions, we included a fraction of massive binary neutron stars in order to see how that would change our results. We found that if there are no massive binary neutron stars, then our energy limits imply an MTOV of 2.15 solar masses. However, if we assume 40% of binary neutron star pairs are massive, like GW 190425, then our limits imply an MTOV of about 2.23 solar masses. This is statistical in nature, and our small sample size does have some limitations to this. Short GRBs are jetted, meaning that we don't see every short GRB that goes off. In fact, we probably can only see 1 out of 100 of the short GRBs that occur in the universe. However, the synchrotron radiation we were searching for would not be jetted, so we would be able to see it even if we didn't detect a GRB. The easiest way to detect this GRB-less magnetar emission would be by utilizing untargeted radio searches, such as the VLA Sky Survey. We can use our light curve modeling to calculate how many of these magnetars should be found by the VLA Sky Survey, based on different density environments. These results are seen in the plot on the left, as a function of number of magnetar remnants found by the VLA Sky Survey versus the fraction of stable magnetars from short GRBs. We find that if short GRBs occur in high-density environments and produce magnetars, we should be able to detect 30 to 300 of these remnants. If more than this number is found, this would indicate that the short GRB population is biased, and if less than this number is found, this would have implications for the fraction of GRBs that produce stable magnetar remnants. We have found that the fraction of short GRBs that can produce stable magnetars is less than 50 to 80%. This is determined by the maximum ejecta energy of our radio observations being less than 10 to the 53 ergs. The low end of this fraction is based on the fact that 13 of the 25 low redshift GRBs, those that are the most likely to have detectable magnetar emission, had energies lower than this threshold. And the high end of this number is based on the fact that 22 of the total 115 short GRBs detected to date had ejecta energies lower than this threshold. So, in conclusion, we didn't detect any magnetar emission from our short GRB radio observations, and only found upper limits on the flux. These upper limits, in combination with our new light curve modeling, show that any extra energy injection from a magnetar remnant would be less than 10 to the 53 ergs for the majority of the short GRBs in our sample, meaning that if a magnetar was produced, it wasn't stable. And additionally, we can place constraints on the maximum mass of a neutron star at about 2.23 solar masses, assuming some of the binary neutron star mergers that occur are massive. We don't actually know the fraction of massive binary neutron stars, but these limits are well in line with the current knowledge of the upper and lower limits of MTOV. Thank you.